Welcome to Section 6C. We're going to be talking about normal distribution. This takes our histogram and superimposes our curve upon the histogram, and if it is symmetric, bell-shaped, meaning that the distribution only has one peak or it's unimodal, and its peak also corresponds to the mean, median, and mode. This is the definition of normal distribution. A couple of examples of something that might be normally distributed is men's heights, women's heights, standardized test scores, men's shoe size, women's shoe size, and so on and so forth. So between my two pictures down here, which one appears to be normal? Well, I kind of already pointed to this one. Notice how I come up, I make a bell curve, I come down, it seems normally distributed, it's symmetric, it only has one peak, where over here it looks like I have two full and complete peaks if I were to estimate with my curve. All right, a couple of characteristics of normal distribution. Here's my picture and the four characteristics. Most of the data is clustered near the mean, or the peak. The data is spread evenly around the mean, which means it's symmetric on both sides. Symmetric meaning that you could fold it in half right on that line that corresponds to the mean, median, and mode. Fold it and it would be the same on both sides. Larger deviations from the mean are increasingly rare. So down here, here's my mean, and larger deviations, meaning the further I go away, become increasingly rare, and you'll see that the height is much smaller, meaning the frequency is much smaller, and it ends up looking like tapering of the tails of the distribution. The fourth characteristic is individual data values result from a combination of many different factors. That means like genetics and environmental factors, which is why these examples of men's heights and women's heights in standardized test scores would be normally distributed. Genetics, there's lots of different variations in genetics, and therefore it would give us a normal distribution. All right, we're going to look at a couple of different examples and kind of think, would that look normally distributed or not? The first one is scores on a very easy test. Now remember, this right here is talking about frequency, right? Each of these, if I were to look at the histogram, would be a frequency of the score below, and we always go with numbers from low to high. So what kind of a histogram or distribution would it end up looking like? Well, if it's an easy test, then I'm going to assume most of the scores are pretty high, right? So they're going to be up here. Very high scores. We will have the occasional low score, so a few low, but mostly very high, which means what kind of a skewed distribution is that? Do you remember? I'm pulling it on the left because it's stretching this way, so it would be left skewed. So not normal, but a left skewed deviation. All right, shoe sizes of a random sample of adult women. Okay, we have genetic factors and environmental factors, so simple random sample, I'm going to say that's normally distributed because there's lots of different factors that can play into the shoe size. So normally distributed. Moving to Roman numeral 2, standard deviation in normal distribution. This is where we hit the 68, 95, and 99.7 rule. That means this. Here's my picture. Within one standard deviation of the mean, and here's my mean right here in the middle, and one standard deviation above and below, right here, is 68. That's where our rule comes from. 68% of the data right there within one standard deviation. And that also follows the characteristics we talked about, which means that most of the data is around the mean. The next is 95. That means within two standard deviations, 95% of the data should fall between two standard deviations. And then, I'm guessing you're probably okay with the next one, 99.7 means that within three standard deviations above and below, 1, 2, 3, 1, 2, 3, standard deviations is 99.7% of the data. Out of curiosity, how much percent of the data then falls out here and out here, because this is talking about all of this is 99.7. So the leftover, the itty bitty little bit of the tail, would only be 0.3% of the data that falls outside of that 3 standard deviation. This is a good rule to have. Write it somewhere, or you can go ahead and print off the formula sheet for the next test so that you have it really close at hand. Now you'll notice this formula over here. We'll be talking about that in Roman numeral 3. It's called the z-score, and it's pretty convenient. We'll get to that later. A couple of things I like to do before I move on in this section is kind of divvy out what percent would fall where. And I think most of you would be okay to do this, but I'm going to walk us through it just a little bit. So if I wanted to know how much data follows from the mean to 1 standard deviation below, I could take, well, if all of this is 68% and I want just this part, I could just divide it by 2, right? And that gives me this portion right here of 34%, and this portion also has 34%, which we just divided by 2. Now, if I wanted this slightly darker tan color, how much falls just here from 2 deviations to 1 deviation below the mean? Well, if all of this data is 95%, and I know that this data is 68%, the fast way to get rid of much of that would be just subtract the 68%, and then I have the data from these 2 shaded regions. So 95 minus 68 gives me 27% of the data that is in between the 1 and 2 standard deviations above and below the mean. So if I wanted just the portion of one of those, I would take that 27 and divide it by 2, which gives me 13.5% of the data will fall in between here, and 13.5% of the data will fall over here. Again, I'll do the same process by finding how much is in this portion right here. So if from here to here is 95% of the data, and from here to here is 99.7% of the data, by subtracting, I'll find out how much is in both of those combined. So 99.7% minus 95% will give me 4.7% of the data is in this and this. But if I only wanted one of those, I could divide by 2. 4.7 divided by 2 gives me 2.35. So 2.35% of the data is here, and 2.35% of the data falls here. And we already talked about how much will fall outside of the 68, 95, 99.7 rule. That's something I would memorize. So say that a bunch to yourself, especially if you're an auditory learner. Now, that's just for convenience sake, because I like to have that, and I've written it down here for you. And you can keep that in your notes. It's kind of nice to have on hand, or you can just calculate it every time again, which works either way. And throughout the lesson, I'm actually going to recalculate it just so that you can see it over and over. But this is kind of for your benefit. Now you'll notice down here I've changed instead of saying -3, -2, -1, we already know that these are the standard deviations above and below the mean. But we're going to go ahead and use some more of the statistical information, or definitions, which is using Greek letters. So this is no longer the mean, we call it mu. This is my Greek symbol, mu, and it represents the mean. If you would like to write this in your homework, you can come up to Insert, Symbol. Mine should be, oh, there we go, under the Greek. This is a Greek symbol, mu. Let's go find it. Oh, there's sigma. That's the uppercase sigma. There's the lowercase sigma. We're going to do that too. You'll see it over here. And there's mu. A bunch of the other fun Greek letters are in here, but we only use those in our statistics. Well, in Math 108 statistics. So here we have mu meaning mean, and it even starts with the same letter, M and M. The next is standard deviation uses our lowercase Greek letter sigma, and it also, sigma starts with S, as does standard deviation. And in this case, we're going to do SAT scores for our next example, where the mean, or mu, is 500, so the mean is 500. The standard deviation, or sigma, is 100. So right here, the mean would be 500, and one standard deviation above that would be 100 points more, making this 600. And 100 points more would make this 2 standard deviations above, which would make this 700, and another standard deviation, or 3 above, would be 800. And I would do the same on the way down, and I can use this minus 1 sigma. I could use that as a formula by saying -1 times my sigma and add that to the mu. 2 of those added to the mu would give me my number for here. So over here I would subtract 100, which gives me 400, subtract another 100, which makes it 300, subtract another 100, which makes it 200. And I actually do this for every single problem I encounter with these ones. I draw my bell curve, I write out my 3 standard deviations, I throw in my mean, or the mu, and then I add and subtract my standard deviations on every single one of them, even if I don't need it, just so that I get practice and I can visually see what the questions are asking me. We are asked in ours, we're given the mean and the standard deviation and interpret it with our rule of the 68, 95, and 99.7 rule. So we already talked about that. In fact, let's go ahead and put those in just for our benefit. This was 200, and I know that doesn't match up perfect. On yours you will. This was 400, and the mean was, let's make that one more centered, 500. Oh, not quite in line with my tab. Add 100 makes it 600. Add another 100 was 700. And add another 100 makes that 800. There we go. Okay, so we need to interpret our SAT scores with the 68, 95, and 99.7 rule. So if 68% of the data is within 1 standard deviation of the mean, that means 68% of all of the scores of the SAT fall between 400 and 600, which, here's our answer. Now we can say that 95% of the data falls between a score of 300 and 700, which is our next answer, and 99.7% of all test scores fall between 200 and 800. All right, let's move to the next one. Vending machines are designed to catch slugs or fake coins by weight. Quarters have a mean weight of, or mu, 5.67 grams, I believe, and the standard deviation, or the lowercase Greek sigma, equals 0.07 grams. They will reject, so vending machines are going to reject quarters that weigh more than 5.81 grams and weigh less than 5.53 grams. So what percent of all legal quarters will be rejected? Because there are some quarters that are worn down just a little bit more, and so they're still legal quarters, but some of them might be rejected. So let's find, the very first thing I always do is draw the bell curve, and I know it's already there, but I would like to go through drawing it with you so that you're familiar, and go ahead and you can do this on your paper for every single one of these problems. So mine's not going to be pretty fancy. I'm just going to draw a curve. Here's my middle, so I know it's mu, up, around, and a teeny curve, and I'm going to give myself my bottom line. Here's 1 standard deviation, 2 standard deviations, and 3 standard deviations. Same on this side. Bring that down a little. There we go. So now I know the that quarters have a mean of 5.67. So I'm going to label that 5. Oops, that's hard to do this. 0.67. Maybe we should reference these numbers over here. Okay, one standard deviation above. So I have 1 sigma here. Oh, that's bad news. And 2 sigmas here. Oh, that's not working very well. We'll just reference these. And 3 sigmas above. Then I have 1 sigma below, 2 sigma below, and 3 sigmas below. So I need to start adding and subtracting my standard deviations to find those numbers. And the standard deviation was 0.07 grams. So to go from 5.67, add 0.07 to get the next one up. 0.07, 7 and 7 is 14, carry the 1. 5.74 is my next one over, which we have here. Add another 0.07, which gives me 5.81, and I could do one more for the 3 deviations above. Apparently I didn't do that on this one. And then I start subtracting. Subtract 0.07 to go below, which gives me 5.6. Subtract 0.07 is 5.53. And again, I could go again. All right, so now the very first thing I always want to do is draw out the standard curve, the normal distribution, label the center, the mean, add my standard deviations, and subtract the standard deviations. Before I even move on to answering any questions, it's very, very helpful. So now that I have it drawn, I can go back and look at the question again. They will reject more than, or coins that weigh more than 5.81. Hey, we found 5.81. That was 2 standard deviations above. And they will reject quarters that are less than 5.53. That happens to be here. So that's within 2 standard deviations on both sides. And we know with the rule 68, 95, 99.7 that within 2 standard deviations, the second one 68, 95. So 95% of all of the frequencies fall right here. So what percent of the legal quarters will be rejected? Well, if 95 fall within those 2 weights, then the rest left over is 5%. So I have 5% will be rejected outside of these 2 deviations. Another way of thinking of it is out here is 2.5 and out here is 2.5, which we found up here. We actually didn't do 2.5, we separated it into one further, but if I were to add those it'd be 2.5 because 95% of the data is within here. So what's left over is 5%. There we go, so 5% will be rejected. The first thing you need to remember is draw the bell curve, the normal distribution, throw in your information, mu, sigma, all of the standard deviations above, all below, and then move back to the question. Okay, let's move on to the next example. Auto prices. Ford Explorers we had 10,000 people were surveyed on the price that they paid for their Ford Explorer. The mean price of these 10,000 people ended up being $16,500 with a standard deviation of 500, which we learned how to calculate in the previous section. And we have 3 questions. The first one is, of the 10,000 people who paid between, or of the 10,000 people, how many paid between 16 and 17,000? The second question is how many paid less than 16,000? And the third question, how many paid more than 18,000? Oh, I forgot, I did want to touch on one little thing up here. Quickly, going back on this example, just in case you might come across it in your homework or the test, these happened to fall exactly within 2 standard deviations. Using our method that we used above, if it told us that we wanted to find that it would reject coins that were from 5.6 to 5.85, we could still do that by using our our method of from here, one standard deviation, 5.6 to 5.74 is 68% of the data. And then we could subtract 95 minus 68 and divide by 2, which would make 68 plus, was that 13.5, and that would give us the percent of all in here. And if we wanted to find the ones that were rejected, we would take 100 minus our 68 plus 13.5. And that's how we would find it if these didn't match. And you can do that by using this as a reference, or you can go through and calculate those again. Sorry, I forgot I wanted to touch on that. Now we'll go back to the Ford Explorers. So the first thing we want to do with this example, they gave us the mean and the standard deviation. The first thing you do is, I even wrote it here, draw your normal bell curve and label it. So I've already done that for us, and I was going to draw it. However, we saw in the last example that doesn't work very well. So we're going to come down here and draw it. There we go. And we put in our sigma and the mu, and then we find those with what they gave us. So the mean was $16,500. That's the mean. So we put that right in the middle. Then a standard deviation of 500. So I'm going to add and subtract my 500 for each and every standard deviation. So adding 500 makes us 17. Adding 500 makes us 17.5. And I didn't put this one here, so let's just go ahead and put it down. Adding another 500 is, 18. Then going down, I subtract 500. So 16 minus the 500 gives us 16,000. Minus the 500 gives us 15,500. Minus another 500 makes this 15,000. And we're going to have to adjust that to make it fit again. There we go. All right, so the very first thing, draw it, label it, get everything ready to go, and then go back to your questions. So now they're asking, the first question, how many of the 10,000 people paid between 16 and 17,000? Here's 16, here's 17. Lucky for us, it matches, and they are within one standard deviation, unlike the example I showed before. If it was a little lopsided, we'd have to calculate like we did previously up on this example. But this one, both of those numbers fall within one standard deviation. So what percent falls within one standard deviation? The rule is 68%. So I know 68% of the people paid between $16,000 and $17,000. Now normally we would just leave it as 68%. However, we were given that 10,000 people were surveyed, so I can find the actual amount of people who paid between $16,000 and $17,000. 68% of means times 68 times 10,000 gives us 6,800 people paid within one standard deviation of the 16,500 within one standard deviation of the mean. Now the second question, since we've already labeled this, I'm just going to copy and paste it down here. And the second question is, how many paid less than 16,000? Okay, so here's 16,000. It's one standard deviation below. And I happen to know that the mean cuts the information right in half, which means from here down is 50%. In fact, we could even change that lower. All of this is 50% of the data. And I know that within one standard deviation is 68%, but I'm only working on the bottom half, so dividing that by 2 gives me 34% right here. So all of the data points to fall below one standard deviation, I can subtract these. 50 minus 34 gives me 16%. So 34 of this, take that away, and I'm left with all of this data over here. gives me 16% of the data falls below that one standard deviation of 16,000. Now remember, they gave me the actual number of people who participated in the survey, so 16% of the 10,000 gives me 1,600 people. Let's move on to the third question. How many paid more than 18,000? Oh, there's our 18,000 at 3 standard deviations. At 3 standard deviations, we know from the 68, 95, and 99.7 rule that there's only 0.3% left on the outside because 99.7 encompasses everything from 3 standard deviations. So out here on the tails, I only have 0.3% left. And the question asks how many paid more, so I only want half of that, this part. So I want to take that 0.3, divide it by 2, and it gives me 0.15% of the data points or people up here that paid above the $18,000. So then I can change this to a decimal by moving my decimal over 2 points. Timesing that by 10,000 like we did previously makes only 15 people paid more than 18,000 for their Ford Explorer. It's pretty fun, isn't it? Let's move to Roman numeral 3, the z-scores, which we kind of showed you earlier up here. We said we'd get to it in Roman numeral 3. The z-score, also known as the standard score. These are really cool, and I have a lot of questions emailed me throughout the next section on how to answer questions, and most of it is because they didn't find the z-score. Now, we've talked about only being at 1 standard deviation above and below, or 2 standard deviations above and below, and 3 standard deviations. That's right on, 1, 2, 3. But what if somebody falls within here? So if you were taking your SAT score, and let's say, do you remember it was at 500 with a standard deviation of 100, so this would be 600. What if you got a 572? Right? So you're not a full standard deviation above. You fall somewhere in the middle. So that's where we get z-scores. This is the number of standard deviation that a data value lies above or below the mean. And it's nice because they aren't always going to fall right on the 1, 2, or 3. So what would the standard deviation, or the standard score, the z-score of the mean be? Well, the definition says it is the standard deviation that the data value lies above or below the mean. Well, the standard score, or the mean, is the mean. So it doesn't fall above or below it at all. It's 0. So the standard deviation, it's 0 standard deviations from itself. So the standard score, or the z-score, of a data value that happens to be 1.5 standard deviations above the mean gives it a z-score of 1.5. It means that it's up here 1.5 standard deviations. What about the standard score of a data value that's 2.4 standard deviations below the mean? That means that it's a negative value. And the z-score would be negative 2.4. And you can kind of see where they get that from, since we have our -1 and our 1 times our lowercase sigma. So if I wanted 1.5, it would be 1.5 sigmas. Negative 2.4 would go down 1, 2.4, negative 2.4 sigmas. Now, here's our formula to calculate the z-score, and I'm going to highlight that just because we're going to come back to it. The z-score equals the data value, subtract the mean, divided by the number of standard deviations. And that makes sense. We want to know how far away the data value is from the mean, and if I divide it by the standard deviations, it gives me how many parts of the standard deviation, like 1.5. If we wanted to rewrite it using our other Greek letters, it's z equals x standing for your data point, subtract mu, remember mu starts with an m, is mean, divided by divided by sigma. S, that word corresponds to standard deviation. So that kind of helps you write it a little quicker. Let's move on to our first example using our z-scores or standard score. It's the same difference. IQ is a standardized test, so the IQ scores are going to be a normal distribution, and the mean of the IQ scores is 100 with a standard deviation of 16. So the first thing we do is draw it. So I've already gotten us this, and I'm not going to try and draw it again. Down here, the mean, or mu, is 100. Standard deviation is 16, so I'm just going to start adding 16 and subtracting it. 100 plus 16 is 116. Add another 16 is 132. Add another 16 is 148. Subtracting 84, subtract 16, 68. Subtract 16 is 52. Okay, now that we have it all laid out so we know what it looks like, let's move on to the question. Find the standard score, or the z-score, of 95 and again of 125. Now I've put little stars down here so that we know these don't actually fall right on the 1 or the 2 or the 3 exact standard deviations. So if you were to have scored, how many standard deviations does that put you above or below mu or the mean? So we're going to take one of these formulas, whichever way you like to think about it. Z equals our data point. We have 95 and 125. So 125 minus mu, or the mean, divided by sigma, or the standard deviation, gives me 25 over 16, which is a decimal of 1.56. So that means that if you were to have scored a 125 on this IQ test, you would be 1.56 standard deviations above the mean. Now if I scored a 95, that's a little down here. 95 minus 95 is your data point. Subtract the mean, which is 100, or mu, divided by sigma, or the standard deviation. 95 minus 100 is negative 5. Divided by 16 gives us the decimal of negative 0.31. That means that you're not a full, not even a half standard deviation below the mean. I think these are so cool. Let's move on to Roman numeral 4, standard scores and percentiles. So what good does it have to know that you're not an exact standard deviation above or below? Well, the standard score, or what we talked about earlier, is we could find the percentages, right? Well, same thing with the standard score, except now we can find a percentile for a specific score. So if you've taken a standardized test, you've probably been familiar with them telling you which percentile you fell in. Parents also get this when they go to the doctor's office, and future parents, it's good for you to know. When they tell you that your child's in the 50th percentile, that means you have a z-score of 0, meaning you're right in the middle. 50% of the children of that height, because they'll give you a percentile for height and weight, 50% of the children are at that or below that weight value or height value for a percentile of 50. So if you have a child in the 98th percentile, which all of my children happen to be in for height, I blame it on Daddy. That means that they are 98.93% of all children at that age and that gender are at that height or lower, like this, than your child. So what's important is for you to be able to find out different kinds of percentiles for test scores or different things like that. Now I got this table from your test sheet. I highly recommend printing this out and having this on hand as you're doing your homework so you don't have to flip back and forth. Also, it gets you really familiar with it so you're not kind of bombarded last minute on the test using something different than what you're used to. If you don't remember how to find that, go into iLearn, click on Course, and go down to the test sheets and go to the one for statistics. All right, so we're going to use this table for our last couple of questions. The first one is about cholesterol levels. Men ages 18 to 24 have cholesterol levels with a mean, or mu, of 178 and a standard deviation, or sigma, of 41. What percentile is a man who has a level of 190 for his cholesterol level? Well, the first thing we want to do is find the z-score. So z-score is z equals the data value, subtract the mean, or mu, divided by the standard deviation, or sigma. So my data value is 190, so it's z equals 190 minus the mean is 178 divided by standard deviation, or sigma, 41. So I subtract first, divide by 41, it gives me 0.29. I'm going to highlight that because that is my z-score, or standard score. But that didn't give me the percentile. So I have to go back to the chart and find this z-score and its coordinating percentile. So I come up here and I need to find 0.29. Here's the z-scores, see they're on the left, and the coordinating percentiles on the right. And I have 0.29. Well, here's 0.30. 0.29 doesn't fit on there perfectly. So I'm going to have to kind of estimate a little below the 61.79%. So I'm going to say just 61 percentile. That sounds pretty reasonable. There we go. So a man who has a cholesterol level of 190 is in the 61st percentile. All right, let's move on to the second question. What cholesterol level corresponds to the 90th percentile? So it's a little backwards. We want to find the data value that gives us the 90th percentile. So we're going to come up and use our chart. I know I've pasted it below, but I would like you to see how we find it in this mass. So we want the 90th percentile. So we're going to use the percentile on the right side, and that's the closest to the 90th that we have, so we're going to use it, and it coordinates with the 1.3 z-score. So now that we have the z-score of 1.3, we can find the data value by working backwards. So we use our formula, z equals x minus mu over sigma, and put in 1.3 for the z-score, but we don't know the data value, or the x. We do know that mu is 178 and the standard deviation, or sigma, is 41. So working backwards, we need to times both sides by 41. So we get 1.3 times 41 equals x minus 178, which gives us 53.3. Then we want to isolate the x by adding 178 to both sides, which gives us 53.3 plus 178 gives us x. So our data value is x equals 231.3. So the cholesterol level of 231.3 is the 90th percentile, not one of the percentiles you want to be in, the 90th percentile for men 18 to 24 cholesterol level. Let's move on to our very last example, women in the Army. Women ages 18 to 24 have a mean height of 65 inches. That's 5 feet 5 inches, which I happen to be, with a standard deviation of 2.5 inches. A woman must be between 58 and 80 inches to serve in the Army, or 4 feet 10 inches to 6 feet 8 inches. So what percent of women are ineligible because of their height? So what I do now in my story problem is I extract my information. I was told that mean, or mu, is 65, so I'm going to write it off to the side just so I have it right there visually for myself. The standard deviation is 2.5 inches, so sigma is 2.5. All right, now I'm going to move on to my question. A woman must be between 58 and 80 inches tall. So I want to find two z-scores that will coordinate with the percentile. And then I can figure out what percent of women are outside of those percentiles. Okay, so the first thing I want to do is find the z-score for 58 and 80. So z equals x, my data, point of 58 minus 65, which is mu, or the mean, divided by the standard deviation, or sigma, 2.5. Subtracting and dividing by 2.5 gives me negative 2.8. Now we'll go look at the percentile in a minute because I want to find the z-score, or standard score, of 80. 80 minus the mean of 65 divided by 2.5 gives me a z-score of 6. Okay, now we can go up and look in our chart for negative 2.8. I know I've pasted it down there, but I want you to see how we find it. Z-score, I know I'm going to be on the negative side, so it's going to be somewhere over here, and I need negative 2.8. There we go. And it coordinates to the percentile negative 0.26. All right, which I've also pasted down here, 0.26 percentile. That means 0.26% of the data is to the left. Remember what it looks like if you're having a hard time. Come up and look at it like this. Negative 0.2 or negative 2.8 is 2.8 standard deviations below, right here. So I'm looking at the percent down here on this very small tail of 0.26 percentile. Now let's find the score that coordinates with 6. Okay, so my z-score goes clear up to 3.5, so 6 doesn't even cover it. So the last percentile I can work with, I'm just going to have to use 99.98%. There we go. Now remember, that's all of the information below that score of 6, or in our case 3.5. So how much we want to know the amount of women who are ineligible. So I want to find the amount of people or of women outside of this range. So how many are going to be taller than my 80 inches? So my percentile, 99.98%, subtract 100, subtract that gives me less than 0.02%. Reason being I'm saying less than is that our z-score was 6. The percentile, the last one we can use, is the 99.98. So I'm going to just say less than that because I would probably have a little bit more, being the z-score is 6. Now, the 58 inches, or my 0.26 percentile, falls outside. So let's come up and visually see it again. So I have my 0.02% way up here because I have a standard score of 6, so it's going to be less than 0.02. And way down here is my other standard percentile, and I want to know the total that fall outside of that. So I want to add them. Adding 0.26 and 0.02 gives me 0.28. But remember, it was a little less than that because I didn't have anything that actually coordinated with the 6. So I'm going to say, added it all together, I have less than 0.28% of women, or about 1 out of every 400, are ineligible because of height. All right, that is our whole section. Good luck, and I hope to see you on the next one.